Session 5. It's got like 4 papers. I'll talk about them in a minute. But I would like, remember that movie, 4 Weddings and a Funeral? So this is 3 proofs and a shared secret. But kind of, in the end, if you follow the shared secret enough, there's something verifiable in there too. So even that is a type of a proof. So it's okay. All right. So these are the papers, but I'll talk about them one by one, and then I'll go through them. Okay. So proofs. We saw some proofs yesterday. We saw relations with locally testable codes and things like that. Today we're going to see proofs that have cool qualities. For example, that a proof that a candidate has a canonical solution. Some of the proofs are going to be really, really super fast proofs, so fast that it's going to be like lightning speed. And some of the proofs are going to be zero knowledge. Okay, so this is the 3 proof papers. The first one is pseudo-deterministic proofs by Shafi Goldwasser, Ofer Grossman, and Diraj Holden. Looks at pseudo-deterministic proofs. Okay, so previous to this work, there was this notion around by some of the same co-authors of pseudo-deterministic algorithms, where you want to find a canonical solution to search problems. Like one of the biggest problems in data science is something called reproducibility. So here there's this notion of reproducibility kind of built into the model. We always want to be able to get the same answer because we want to reproduce the results. So this is a fantastic notion, and now we have extended it to the notion of interactive proofs. And now we have a prover that can help you prove that a solution is a canonical solution. And here they get some very cool results. So first of all, they define the notion of pseudo-deterministic interactive proofs. Really cool. And then they get some cool results within this new model. For example, they show that you can get a search version of graph isomorphism in constant rounds. So there's a really interesting problem that that can be done in this type of model. They also show other results. I won't be able to show all of them, but I'll just mention one more. NP is not likely to have constant round pseudo-deterministic proof system. They look at a logarithmic, non-deterministic logarithmic space, and more and more and more. So these are really cool results in a couple of minutes. In contrast to yesterday, it's a little bit different. Yesterday we talked about proofs where you prove that some W is unique. Here, you prove that W is a canonical solution. It's very different. Okay. Second, I want to talk about another question. What about the paper Simply Doubly Efficient Interactive Proof Systems for Locally Characterizable Sets by Goldreich and Guy Rothblum? So we've seen proofs. We talked about them yesterday. We talked about them for years. These are fantastic proofs where you have very general protocols for all of IP and P space, where a prover can convince a verifier that a solution is correct. Okay, so this is amazing. It's great for delegated computation. It's something that is extremely powerful and extremely general. Now, the issue is because it's so powerful and so general, these protocols, it's kind of one size fits all. So now the question is, if for a specific problem you're looking for a better protocol, can you do a lot better? And the answer is, this paper says yes, we can. So they look at the questions of clique and T-sum, and they actually give something in the doubly efficient framework, meaning that there's a nearly linear time verifier, and the prover, these are polynomial time problems, the prover is also polynomial time. So we don't, for this polynomial time problem, we don't need the p-space ability prover to prove something to us. We can just get a polynomial time prover to prove this to us, and we can be extremely fast. We're like a nearly linear verifier. So this is really good when you want to do when you want to do delegated computation on really massive inputs. Okay, and in addition, I think another really interesting thing about this paper is it works on developing an algorithmic toolbox for creating good proof systems, and it comes up with really cool techniques. And so there's a very cool sum check protocol in here that allows you to do all kinds of things faster and better and simpler and nicer, and it's just nice. Okay, so third paper on proofs is Zero Knowledge Proofs of Proximity by Itai Berman, Ron Rothblum, and Vinod Vaikunthanathan. Here, we were talking about something that we mentioned yesterday, proofs of proximity. We're asking, is an input close to being in a language L? Can the prover help me convince me of this, okay? So I've got this input X. I want to know whether it's close to being in the language L, meaning, and what do I mean by close? I mean, if I change a few bits, does that help me put it in the language L, okay? And I'd like to know, I'd like to believe this is true, and there's some prover out there helping me. Furthermore, it's a huge input, just like the previous paper. It's a very, very large input. And actually, it's so large, I don't really have time to look at the whole input. So I'm a sublinear time verifier, and there's this prover out there helping convince me that this input is close to being in the language L in the sense that I could just change a few bits and make it be in the language L. Okay, so now we knew there were some works on this problem, okay? So this is something that has been studied at length by some of the people in this room. But what if I also want zero knowledge, okay? And in particular, you know, I'm like looking at a few bits and it's a large input. And because I'm looking at a few bits, I don't really learn a lot about the input. Okay? So now I want to say, actually, this verifier, he doesn't really learn that much about the input other than the fact that it's close to being in the language. I'd like to somehow formalize that. How do I formalize that? Not clear. So this is the first paper that actually tries to do that. I mean, does that. This is the first paper that does that. Actually, this is a paper this is a problem I actually thought about 17 years ago, and I had no idea how to do this. So it's not clear. So I want to say that this question of how you even define this is not clear. I mean, it's not that obvious. It's not obvious at all. And the fact that the verifier sees a few bits doesn't mean it doesn't learn anything. So how do you get protocols that do that? Also, not obvious, okay? Just because you see just a few bits, you're not supposed to learn anything, okay? So nothing here is obvious, not in the definitions and not in the solutions, okay? So what they show is how to define it. They give a problem for which these types of zero knowledge protocols are exponentially faster than trying to go it alone by yourself. So like if you tried to compute it by yourself, it would take you exponentially more time than having a prover convince you. And they look at a lot of cool problems such as graph expansion, bipartiteness, and then they also give general construction. Okay, so now, you know, for the secret, I hate to make the analogy with secrets and funerals, so let's skip that analogy. But so there's this paper on foundations of homomorphic secret sharing. So this is the kind of the ultimate paper of the session by Alette Boyle, Niv Gilboa, Yuval Ishai, Rachel Lin, and Stefano Tesaro. And here we're given a function. Okay, so what's homomorphic secret sharing? Before we get into a homomorphic secret sharing is you're given F, a client shares X to multiple servers. The servers homomorphically operate on these shares, and then somehow from that we want to reconstruct the function value at X. Okay, so nobody's supposed to learn anything. Like these guys are supposed to help you compute, nobody's supposed to learn a thing. Okay, so this paper kind of unifies and extends all the previous definitions, and they give bad news and good news. Okay, so bad news that they give is there's no information theoretic homomorphic secret sharing scheme for, it's hard to say this, homomorphic secret sharing scheme for inner product or disjointness. So in general, there are problems which are hard. It's also unlikely to be able to construct multi-input homomorphic secret sharing from generic primitives. They give evidence of that. But they also give good news, which they show that these HSSs can be used to construct improved two-round multi-party computation protocols. And even more interesting is they show this cool connection between worst case to average case reductions in P. So it has a relationship with fine-grained complexity. Okay, so with that, I'm done ranting.